May June 20 paper 4.2. This is the COVID-19 cancelled variation paper, but never mind, we can learn from all questions. And in this question, we are going to look at gravitational potential and the change in potential energy of a rocket that is orbit around the Earth. Okay, so let's start by answering the question. So as usual, normally if they ask for definition in this topic, there's only quite a fixed few definition, and here they ask you to define gravitational potential. Phi, yeah. So gravitational potential, normally there are 2 points. The first thing that you will write is this is work done. Not just work done, it's work done per unit mass in bringing it from infinity to a point in the gravitational field. Okay, so check out the lecture video where we went deep diving into why we define bringing it from infinity. The short answer to that is gravitational potential at infinity is 0. So we start measuring from 0, which is great. Okay, so part B. An isolated solid sphere R, radius r, may be assumed to have mass m concentrated at its center. So this one is the standard things law. They will tell you stuff like, oh, the mass is behaving that way, yada yada. Okay, no problem. In figure 1.1, show the variation of gravitational potential with the distance d from the center of the sphere for values of r to 4r. Okay, so if let's say you are a visual person, you may want to, at least during your practice, try to draw out where the sphere will be. So 0 here is the center of the sphere. Okay, so to give you a bit of context about what we're talking about, 0 here is the center of the sphere, and I'm going to just draw out a sphere just to, contextualize the question. My beautiful friends, could change color. Okay, so let's say this is my, oh no, radius is here. Okay, this is a big planet. Okay, there we go. All right, so purpose of this is more of like to give you an idea of how things are. All right, so this is the radius, sort of. Yep, I'm going to place it a bit higher. Okay. So this part here will be on the surface lah, something like here. Okay, so when you visualize this, I'm trying to draw it as accurate as possible to help people, but this is the radius of the sphere and the sphere is from here. So you are asked to draw from R, because this is D, we are traveling away from the planet. The blue color circle is the mass or the planet, and we are measuring D from this point. So D is measured outwards this way. Okay, so first things first, we need an equation for gravitational potential. So you recall that gravitational potential is negative gm over r. So from here, I can tell potential is inversely proportional to r, because g is a constant and mass of the planet, this big M here, my big boy here, is constant. Okay, so if everything is constant and is inversely proportional, it also says here that the magnitude of the gravitational potential at the surface is phi. So that means this is at the surface, and at the surface will be at this particular point here, 1 phi. But miss, should I draw positive or negative? Of course, you should draw negative lah. You see the negative here? Okay, because it says here the magnitude. So magnitude is phi, but the actual value is negative. So if you think of plotting here, you'll probably lose 1 mark. So I'm going to shift it down and we're going to draw negative. This is very important because it tells us a fundamental property of gravitation, which is it's attractive. All right, so I'm going to start with negative. Okay, and then right now, we're going to continue. What happens to 2r? 2r Okay, let's say you generally don't really know what to do with this directly proportional, inversely proportional thing. Okay, you could just use ratio lah. Okay, so when the gravitational potential is negative phi, the value of D is R. Okay, so we're going to write this in the equation. Okay, so let me rub this and write it in the equation for you. Of course, if you understand this, you can use the timestamp to skip ahead and watch the next part. All right, anyway, so this one would be negative GM over R. Okay, now let's try 2R. At 2R, your potential is negative. So let's say this is potential 2R. GM over 2R. So you will notice that this negative 1 over 2, this is GM over R. Correct? And ladies and gentlemen, this negative GM over R is this negative GM over R. So from here, you can find that the potential at 2R is actually equal to potential over 2. Okay, of course, negative lah. Okay, so then I'm going to plot here. Okay, 0.5. Okay, what about 3? Same idea lor. If you still need a bit of help, don't be shy, do this again. The potential at point number 3 is negative GM over 3R. Okay, it won't suddenly become positive one lah. Potential is always negative. So this will be negative, and you can see this GM over R is here. So this will be negative original potential divided by 3. So this is what we mean by potential is inversely proportional to radius. Does that make sense? So if the potential goes from, if the radius go to 2R, the potential go to divide by 2. If it goes to 3R, then this one will go to divide by 3. Does that hopefully that makes sense? Okay. So this proportionality relationship is pretty important because different chapters in A2 may ask you to draw different graphs. But if you can see this and instinctively can draw, very good. Okay, so what is 1 over 3? 1 over 3 is about 0.3333333. So I'm going to continue this. 0.1, 0.2, 0.3. 3.3 is close to 3.5, so I'll plot a point here. Okay, and I think you will be able to tell me what happens when R becomes 4R. What happens to your potential? It will divide by 4. Okay, so hopefully you can see the progression. So we'll divide by 4. 1 divided by 4 is 0.25. So I think I will, because this is paper 4, I can plot in between boxes. Okay, so I'm going to emphasize here again. Okay, so plot in between boxes allowed for theory paper, which is paper 2 and paper 4. Not allowed for paper 5 and paper 3. Won't say not allowed, ambiguous. Okay, so the idea of in between boxes, paper 4 can, theory can. Alright, so try your best to plot in the middle. Because this graph is 3 marked, so every point matters. So once you have all your points, okay, then you can take out a pencil and join them in a smooth curve. Okay, so we'll start from 1 to 0.5. Draw together with me lah. 0.33. Okay. I guess it would look nicer if I adjust this to half a box. 0.1, 2, 3. 3 will be in the middle here. Okay, anyway, as long as the curve looks reasonably smooth, you are okay. All right. So yes, that is what we will do for this part. Okay, so good enough lah. All right, where are the marks? I'm going to use red for this to show you where the marks are. Okay, so 1 mark is when 3 marks, right? So 1 mark is when you have gradient. Okay, I'll tell you what, I'll just crop the mark scheme. Ding, ding, ding. All right. So your curve from R to 4R with gradient of decreasing magnitude and start at R plus minus potential, 1 mark. So the curve and the shape is 1 mark. The line passing through this point and this point is 1 mark. Okay, and then the line showing that the potential is negative throughout is 1 mark. So if you drew the positive here, you will get 2 out of 3, which is not that bad. Okay, so don't leave the sketching stuff empty because they're generally quite straightforward. Okay, so normally 1 mark is for the shape. If you want to know what the general comment is 1 mark is normally for the shape of the graph. 1 mark is for the important values, coordinates. And no matter what graph they ask you to sketch, important coordinates. Okay, so these are all important coordinates that I can plot out. Why they didn't put 3R? Because 3R is a bit the weird one out, but I include it there as well. And then the other mark is normally for polarity. Either is positive or negative. Okay, so normally you just ask yourself, is the shape correct? Is the coordinate correct? And is it supposed to be always positive, always negative? Position of the curve, is it correct? That will probably help you with your sketching, right? So that's this one. I'm just gonna park this here. I spent some time talking about this. Okay, so make sure you are clear with how to deal with a relationship that looks like this. Okay, we're gonna move on now. Part C. Okay, the sphere that we analyzed just now is a planet with radius this much. Okay, if you do enough gravitation question, you immediately can identify this is Earth lah, our mother planet. Okay, and the mass this much. Planet has no atmosphere. Okay, so if there's no atmosphere, means there is no energy loss to friction. Right? So there's no friction. Whatever energy conversion, there's no energy loss to friction or air resistance. So we have a rock of mass 3.4 times 10 to the power of 3 kg. So this is my rock. And it moves directly towards the planet. Oh no. Its distance from the center of the planet changes from 4R to 3R. Calculate the change in gravitational potential energy of the rock. Okay, so in this kind of question, right, if they didn't give you a graph, I mean, they did ask you to sketch, but if you look at this graph, you don't really have any values, right? You just have the value at the surface and the fractions of all the values after that. So because you don't have those values, right, it is immediately evident that you have to use equation. You cannot read from the graph as some other examples. Okay, so first things first, we ask ourselves, what is the equation for gravitational potential energy? Gravitational potential energy at any point, GPE, I'm just going to call this EP, okay, is equal to negative G, mass of the planet, mass of the rock over GMM over R. Okay, and if it helps you, I will draw out the planet, okay, and we are bringing the rock from, okay, so this is R, 2R, 3R, from 4R to 3R. So carrying it from 4R all the way to 3R. This is M, this is big M. Bloop. Okay. Change in gravitational potential energy from here to here. Now, first things first, if I'm a student, right, I'm thinking, if I'm traveling closer to the surface, do you think your potential increase or decrease? You drop something, when it travels closer to the ground, the potential decrease, right? So I fully expect this change to be a decrease. This change is a decrease. And I would be happier if my final answer got negative sign. Okay, but let's see. So you want to find the change in potential energy. I will take the final potential energy, the potential energy at 3R minus the potential energy at 4R. Okay, so always take always take final minus initial. Makes sense, right? You want to find the change, so you take the final form minus the initial form. So I can now substitute the equation. Okay, so this is negative G. Miss, you don't substitute value first. No, I don't do that first one. I put the equation first because I can factorize. Okay, negative GMM over 4R. Okay, take note that I'm careful about the sign. This one is this thing, 3R, including the negative sign. Okay, and then this 4R is this thing. The negative there, the minus there is this one. Okay, all right, so let me simplify a bit to prevent sign error. I'm going to factorize GMM over R. Is that okay? Because those are the common factors, big bracket. Okay, negative is positive. Okay, so I'm going to have 1 over 4. So I've taken out GMM over R. So what is left is 1 over 4. Negative becomes positive 1 over 4. Minus, this minus will be from here. GMM over R I've taken out. So what is left is 1/3. Yay. Okay, now we can substitute. 6.67 times 10 to the power of negative 11. Mass of the planet, let me copy. 6.0 times 10 to the power of 24. Mass of the rock, this is a very heavy rock, 3.4 times 10 to the power of 3. Okay, and I have 1 over 4 minus 1 over 3. Divided by, what is R? Where is my R? 6.4 times 10 to the power of 6. Okay, so it's pretty important to simplify the equation. Do it slowly before you bring in all these prefix, and then when you bring in the prefix, it clutters up the equation, and you want to avoid errors as much as you can. All right, so hopefully you're pressing the calculator with me right now. Ta-da! Again, I want to show people how to press calculator lah. Okay, so I'm going to start from, I'm going to key in what I see. Okay, and I don't really have to use brackets because there are no plus or minus, addition or subtraction things except the fraction. 4 times 10 to the power of 3 multiply by, then only you bracket 1 over 4 minus 1 over 3 divided by 6.4 10 to the power of 6. So let me double check to make sure all the values here are in SI. Yes, no need to convert anything. Okay, very good. I press equal now. So this value, I'm going to write here, okay? Negative 1.77 times 10 to the power of 10 joule. Okay? Then you might be thinking, why got negative? Nah, remember when we started this discussion, we know that this one is a decrease in GPE, which makes sense because your M is moving closer to the surface, closer to the planet. So if it's moving closer, GPE should decrease. Okay, so here I will write the answer, 1.77 times 10 to the power of 10 joule. Means I put positive can. I put negative can. Doesn't matter. Because whenever they say change, it just generally magnitude is enough. But I like to flex lah, so I'm going to put a negative here. And then whenever there's a negative, I will put a side note here to explain to the examiner like this. The negative here is not a calculating error, okay? I know why there's a negative. I expected the negative. It's because the potential decrease. So whenever you look at mark scheme and you feel that you should write a negative, just try to examine whether the negative is necessary or not. So for example, in this case, if it's a change, now I'm going to be transparent to you and I'll show you the mark scheme now. They did not specify that you need to put negative here. So you can take the bigger potential energy, which is the one at 4R, minus the smaller one. But both values are okay. You want a positive also can. Positive is only the magnitude. Negative is a more accurate description because it doesn't only tell me how much it changed, it also tells me information about whether it decreases or increases. Okay, and it sometimes can be important if you continue the question to part 2. Okay, so just for you, I'm going to draw the potential energy against distance graph. Okay, so from 4R to 3R, your potential energy will have the same kind of graph as your potential graph, because one is potential, gravitational potential, which is energy per unit mass, and the other one is energy. So you kind of expect something like this, right? So that's why when we travel from here to here, when we travel from 4R to 3R, this traveling down this curve shows a drop in GPE. So if you actually understand and internalize this graph in your head, right, it actually makes perfect sense. You know why the GPE decrease. Moving closer to the planet, this value is always negative, etc., etc. So keep the negative if you need it. All right, part 2. Explain whether the rock's speed increase, decrease, or stays the same. Okay, I guess in this question, you need to ask yourself, if I want to find the kinetic energy of the rock, what should I do? Well, GPE decreases, right? So I can say the rock loses gravitational PE. So energy cannot be destroyed. So it has to be converted to another form. So the question would be, convert to what form? Rock loses gravitational potential energy. Friction can? Cannot because there's no atmosphere. See? The question says there is no atmosphere. So what do we do? So the only way it can go is loses gravitational potential energy, which is converted to kinetic energy. Okay, so loses potential energy, which is converted to kinetic energy. So because of this, hence, you can say kinetic energy increases. So we expect the rock that is dropping or going towards the planet to be faster and faster, and then maybe crash into the planet and cause a mass extinction. I don't know. But that's the question. Okay, so where are the marks? Okay, let me mark the whole part for this one first. 1 mark if you apply the right GPE equation. So generally, I tell students, if you are familiar with the mark scheme, right, whenever they ask you to calculate this, you just write your insurance plan first. My insurance plan is potential energy is negative GMM over R. So if we see this, immediately we will give you 1 mark already. But miss, if I didn't write this, never mind. I look at these 2 expressions, I know you are applying the same equation. So I can give you marks already. So there will be a mark here. Okay, and there will be another mark if you substitute everything correctly. So these are C1 and C1, calculation mark, and this is answer 1. The negative is optional. Okay, I like to put a negative, and I like to explain to the examiner why I put a negative, because it shows a decrease, and you will not be penalized by that. Or you could stick to positive because they want change, so it doesn't matter. All right, this one, if you mention the GPE decreases, loses GPE, or KE increases. So let me write here. Loses GPE or increase KE. Okay, so this one is 1 mark, B1. And the final one, oh, kinetic energy increases. So here, I mentioned already. I didn't answer the speed part, my bad. Hiya, speed. So hence kinetic energy increases. Speed of rocket increases. Yeah. So the mark we are looking for is either you mention loses GPE or increase KE. Then the final one would be speed of rocket increases. Let me check the nature of the mark first. They are all independent marks. So sometimes this speed increase depends on whether you can justify or not. If you cannot justify, you will not get 2 marks. But in this case, they allow both, which is beautiful. Okay, so that's it for this particular question. We have to be a bit more specific, especially when sketching the graph. So I spent some time talking about this. Because sometimes you're like, okay, I know how the graph looks like and it's fairly straightforward. But actually, it's not just pen and draw, unless this is 1 mark. So check the square bracket. If it's 1 mark, we generally, the tip I can give you is look at the marks. Because when someone sets a paper, they will tell you indirectly how much time you should spend in a question. The general rule of thumb is 1 mark, 1 minute, not including reading the question. So you read the question, you understand it, and then when you want to start the question, you should roughly spend about 3 minutes. If you spend too much time, then you're running out of time. Okay? So that's the intention of this question. They give 3 marks because they want you to pass through everything. And the reason why potential is negative is important because this shows, I'll write here for you, this shows that gravity is attractive. So it's a very important property of gravity that it has to be shown inside the graph. Okay, so this is to show G field as attractive. And just as a recap, when you explain this, gravitational field is attractive and work is done by the gravitational field to bring it from infinity. So when you want to bring a rock from infinity, gravitational field will help you bring it over, okay, as mentioned in the lecture. All right, so that's it for May, June 20, a rock approaching the planet's surface.